Hello everyone. In the previous video, we discussed about Coulomb's law, which gives the force between two charged particles separated by some distance in a medium. And the expression is like this. As I promised in the previous video that we will solve one problem from previous year, let us solve one problem. This problem came in HS 2015 for 2 marks, and here they are asking us to find magnitude of electrostatic force between a proton and an electron separated by a distance of 0.5 angstrom, and the magnitude of the charge of proton and electron is given here, and the value of the constant is given. So the first step to solve a problem is to write what are the parameters are supplied to us. So here we have to start like this. Here R is 0.5 angstrom. Now you can see that angstrom is not the SI unit, so we have to convert this into SI unit. So 1 angstrom is 10 to the power minus 10 meter, and this will give us 5 into 10 to the power minus 11 meter. This decimal I absorb it here, and the magnitude of the two charges are equal, and the value is 1.6 into 10 to the power minus 19 Coulomb, and we have to find out the force. Then we begin like this. We have F is equal to 1 by 4 pi epsilon naught Q1 Q2 by R square. Then we put the value. This value, as we know, and it is also supplied in the problem. Okay, 9 into 10 to the power 9. But sometimes this value may not be supplied, so it's better to by heart this value. So we put the value of the charge, 5 into 10 to the minus 11 whole square. The first step to solve a problem like this is to write the whole numbers together like this, and this will give us 25, and write the powers together. This 9 here. Here I am applying the law of indices. This it will become 22. When it comes here, it will become plus 22. This will give us 2.56. 16 into 16 is 256 divided by 25, and here I will get 9, and 22 is 31 minus 38, and you can see that 2.56 and 25, they are nearly equal, so we can do a approximate calculation, and this will give us 0.9 10 to the minus 7, and this one we can write like 10 to the power minus 8 Newton, like this. This type of approximation calculation are allowed. Approximate calculation are allowed. It is to solve problem, but if it is too much, if it deviates too much, better to do it in the proper way. So to save time, I have done this approximate calculation. So our next topic today is forces between multiple charges. That means what will be the total charge or total force on a charge if there are other charges nearby it. So in order to find that force, that total force, we have to apply the principle of superposition. Here is this principle of superposition. According to principle of superposition, the total force on a charge is the vector sum, mind the word, vector sum of the forces due to other charges. So let me explain this. Let us say I have one charge here, another charge here, and I want to find the force on this charge. Let us say Q0. There can be any number of charges, so we need this distance. So let us say this distance is 1 0, distance from Q1 to Q0, and this distance from 2 to 0. This will be the direction of force if both of them are of same sign. If both of them are positive, then this will be the direction of repulsive force. So we write like this, F2 here, and this force we write like F1 here. Then the total force is the vector sum of this. This total force is the vector sum of the forces on this charge due to other charges. So this expression we can write like this: Q1, Q0, distance between them is 1, 0 square, and this direction part we have to write because it is a vector quantity, like this direction we need, so like this. So this will give you the force, total force. So there are two problems given here to find the total force. The process is very similar. We find out the force on, let us say in this example, they are asking us to find the total force on this on the centroid placed at the center of this equilateral triangle. We find out the force on this due to this, the direction will be like this. Force on this charge due to Q2 will be directed like this. They are of similar type. That is why the force of repulsion has a direction in this way. Similarly, force on this due to this is in this direction. And then we take a vector sum of this. The next topic that we need to discuss is electric field. See, electric field is a very useful concept. The question was like this: suppose I have a charge here. We all know that if I bring another charge, it is going to get repelled if they are similar type of charge, or if it is opposite, there will be attractive force. Now the question was like how this force is exerted, and to answer that question, concept of electric field was given. Electric field intensity. Simply we say electric field is defined as force experienced by a unit positive charge. That means this charge has to be 1 Coulomb. If I take any other charge, I have to divide by the amount of charge here. There is a condition that this charge should not be large. It should not disturb this charge. If I place a very big charge, it will affect this. That should not happen. So this charge should be very small. So the way of writing this is like this: limit of Q0 tending to 0, then force per unit charge is defined as electric field intensity. So this force is given by the Coulomb's law. This force is nothing but the Coulomb's law. So let us write that also. Force is 1 by 4 pi epsilon naught. One charge, the other charge, we have to multiply them, and then square of the distance between them. Let us say this distance is r, and the direction part will be there, into this 1 upon Q0 is there. So we can cancel this. Since there is no Q0 here, after cancelling this, we do not need to write this again. So we can simply write like this: Q by r square with a r cap. So this is the expression for electric field at this point. Now the next question is, since electric field is a vector quantity, what will be the direction? The direction of electric field at a point is along the direction of the force. So if the force is this side, electric field is also in the same side. Okay, and it is easy to remember. Electric field due to a charge is 1 by 4 pi epsilon, the charge itself, and the distance square. The next thing is that if I consider this point, direction of field will be this side. Let us say the distance is same. Let us say that this distance is same, like this. So it means that magnitude of electric field here will be same as that of this, but direction will be different. And for a vector quantity, if direction is different, the vector becomes different. So that is why electric field will be different at different points around it. If the distance is less or more, magnitude is going to be different, and direction also is going to change. So we can say that electric field is a function of the position vector of the point where we are calculating it, and it's a vector field. Is a vector field. Okay. So while this formula in scalar form, we write it like this. Electric field is equal to force per unit charge. So this is important formula. Now, like, what will be the unit? Unit of electric field is force per unit charge. So force is measured in Newton, charge in Coulomb. So unit is Newton per Coulomb. Okay. In the same way, you can find out dimension also. Dimension will be, force dimension is m1 l1 t minus 2. Charge is at. So after combining this, you get m1 l1 t minus 3 a minus 1. So they are also important. This is important while solving problem. You have to write the unit, and dimension sometimes come for 1 marks. Okay. Then some properties of electric field is given here. Here the second property says that uh, electric field is a vector field. This one I already explained in the previous page. And then for a positive charge, electric field will be directed radially outward from the charge. If it is negative, it will be inward. The meaning is that if it is a positive charge, a unit positive charge is going to get repelled in this direction, or in this direction, like this. So these are radial direction. So for a positive charge, electric field is directed radially outward. If it is a negative charge, a positive charge will be attracted towards it, and that this will be the direction of force, and this will also be the direction of electric field. So you can see that they are radially inward. For a negative charge, it is radially inward. And then electric field, due to a system of charges, if we need to find out the electric field due to a system of charges, like we have done in the previous topic. Suppose we have a charge configuration and we need to find the electric field at this point due to these all charges Q1 and Q2. What we can do is that we can follow the principle of superposition, according to which electric field at this point is vector sum of the electric field due to this charge and electric field due to the other charge. So in simple word, if we find the total force, we just divide by the amount of charge here. We get the electric field at this point. So we can say that total electric field and total force at a point follows principle of superposition. Okay. So it means that if you had solved these problems and you suppose you had find some value of force, you can easily find the electric field also. Just divide by the amount of charge. Then physical significance of electric field. I already told you that using the concept of electric field, we can explain how force between two charged particles arises. The concept of electric field becomes very interesting when we discuss about electromagnetic wave. This is electromagnetic wave. Here we can see that there is an electric field which is varying or changing with space, that means with distance, as well as with time. So whenever electric field varies with time, it produces electromagnetic wave, and electromagnetic wave is very important. It is being used in mobile phones and for communication. Even the light is also electromagnetic wave. We will discuss about this in the last chapter of this book, which is electromagnetic wave. So next topic that we need to discuss is electric field lines. Electric field lines. So let us go back to this example. If I put this charge here, it will be repelled along this direction. So I can say that this is the direction in which a charge will move in the electric field produced by this charge. This type of charge is called a source charge, and this one is called test charge. So electric field lines are the direction in which a unit, we have to take unit positive test charge so that the value become 1 coulomb in the electric field of another charge, if it were free to do so. That means if this charge is free to move, whatever direction it is going to take is the direction of a field line. So like this, there can be many directions, so there can be many field lines like this. It also means that for a positive test charge, for a positive source charge, electric field lines will be radially outward, and for a negative charge it will be radially inward. Now there are more to electric field lines. Let us say the another important point of electric field line is that it gives you the direction of the net electric field line at that point. The meaning is that, let us say I have a negative charge here. For this negative charge, the field line will be like this. This field line will, these field lines will be forming like this. Like this. You can see this figure here. Okay. So these all figures are important. All these figures are important. So here we can see that if I put a test charge here, it will be moving along this direction. And if I draw a tangent to this field line at this point, say I draw a tangent to this point at this field line, this will give me the total electric field at this point. Mind it, total electric field at this point. Okay, that means the vector sum of the electric field due to this positive charge and this negative charge, whatever direction it will have, this tangent will point in that direction. And from here we can say that electric field line starts from positive charge and it ends in negative charge. So that means what, they are starting from, they are not continuous curve, they are starting from positive and merging at negative charge. If there is no negative charge, then what will happen? In that case, let's say here, if there is no other charge here, then the field line will end at infinity. It will end at infinity, and for negative charge it will start from infinity. And if there are two charges, it will start at positive charge, it will end at negative charge. So properties of field lines are, these are the properties of field line, page number 25. These are very important, these four properties. So here these properties are like, more the field lines, stronger is the electric field. You can see near the charge field is stronger, and there are a lot of field lines here. Away from, if you consider this point here, if you consider this area and this area, same area, you will get more field lines here. This field line, number of field line will become less here. So we can say that more concentration of field line represents stronger electric field. Okay, so please follow these four properties. The next topic that we want to discuss is electric flux. Electric flux. Okay. Oh, one more thing. These field lines are imaginary concept. These are imaginary lines along which a test charge may move if it is free to do so. Now electric flux is a physical quantity represented by phi, which gives number of field lines passing through an area. So the definition is like this. Say I have this area. This is a three-dimensional figure. Okay, so it's like this. Suppose this is the area. So I have tried to draw it in this manner here. The direction of this area is perpendicular to it. That means if this is the area, direction will be this side, perpendicular to it. And let us say there is a uniform electric field. Uniform electric field. Uniform electric field is represented by field lines which are parallel like this. So like this. So here the flux is given by this formula. Actually this is a general formula for flux. So according here we have a dot product, and when we remove this dot product we get like this. So what is this theta is? Theta is the angle between electric field and area vector. Area is a vector, its direction is perpendicular to the surface. So in this case the angle between E and A is 0 degree here, and flux will be EA cos 0 degree, which is EA, and this is the maximum value. So that means if the electric field lines are going like this and I put the area like this, all the field lines is going to pass through this, and that will be the maximum flux through this area. If I keep the area like this, then minimum number of field line will pass. So that is the next concept here. Suppose these are field lines and I put the area like this. This is the direction of this area. This is the direction of electric field. So this makes angle 90 degree here, and flux will become EA cos of 90 degree. Cos of 90 is 0, and we get EA into 0, that's 0, and this is the minimum flux line. Okay, and then SI unit of phi. So phi is defined like this: EA. Electric field has a unit Newton per Coulomb. Area has a unit of meter square. So this will be the SI unit of phi. And then dimension of phi. E has a dimension m1 L. Let us see what is the dimension that we have calculated already. M1 L1 T minus 3 A minus 1. M1 L1 T minus 3. This is the dimension of electric field. Area dimension is L square, and that will give us M1 L2 like this. This is the dimension. This is the dimension of flux. Okay. So I have seen problems based on flux. Okay. So you try to follow the question papers and try to solve the problems. They are simple. Only you have to apply this formula. Okay. Let's hope you are able to follow whatever I'm trying to convey. If you have any doubt, you can drop a comment. Drop your doubt at the comment below. Thank you.